Generations of integrated circuits. So mainly there are five generations of IC. Typically four. Some may more segregate it as five. SSI, which speaks of small scale integration. So different planar devices, logic gate,
Sir, can you please repeat? Your voice was not properly audible.
so we have started with generations of IC. Small scale integration. SSI speaks of small scale integration. Small scale integration, which exemplifies the planar devices, logic gates, flip-flops, etc., which typically comprise of around 10 to 20 transistors. Now it is audible. Voice is audible now.
Yes, sir, it's
Okay.
audible.
Then comes MSI or medium scale integration. Medium scale integration. So what are the example devices? Counter, multiplexer, adder, etc. So different small sized computational devices which has a number of transistors 100 to 200 transistors. Then the next generation is VLSI, large scale integration. The examples are 4 to 8-bit microprocessors, random access memories, etc. With a number of transistors ranging from 1000 to 10,000. Lastly is VLSI, which is very large scale integration. Where the number of transistors are in millions. So 10,000 to there is no limit. So the examples are 16, with 32-bit microprocessor, high density RAM, and so on. So ultimately, this evolution of integrated circuit from small scale integration to medium scale, from medium scale to large scale, and from large scale to very large scale integration did not occur in a short time. Rather, it started in 1960s and moved beyond 2020. Now, I did mention in last day that there is a very important hypothesis or prediction done by Gordon Moore, typically named as Moore's law. Even though this is not a law, because there is no mathematical proof, what he predicted right in 1965-66, around that era, that the number of transistors per unit area of a chip shall double every 2 years. So this was a mere prediction, but surprisingly, this prediction became true since the last 50 years. So even there were certain situations when the number of transistors increased in a much rapid rate, maybe every 1.8 years, even less than 2 years. So based on this Moore's law, the whole semiconductor industry stood very strongly since the last 3 to 4 decades. And why this is not a law? Because it has no mathematical proof. It is just a prediction based on how, at what degree of miniaturization you can create the semiconductor devices. Because the smaller the sizes of the transistor, higher will be packaging density. Smaller the sizes or the size of a transistor, higher will be its packaging density. And per unit area of the chip, you are always considering the per unit area of the chip, means you are considering the density at which you can package those transistors. And ultimately, Gordon Moore's law paved the way for these very small sized computational devices. So the size of a computer reduced manifold thanks to the prediction of Gordon Moore. So So as Moore's law became a phenomena, the size of a computer reduced to what we find it today, from the size of a large size room. So this happened in the last 40, 50 years. Now, what has been observed since 2010 or maybe 2005 or 6 onwards itself, the deviation of Moore's law. Even Gordon Moore acknowledged in the year of 2000 something 7 or 8 that yes, his prediction or hypothesis is not followed nowadays. So this occurred due to the physical limitation of the size of an atom, because ultimately a transistor channel length can't reduce below the diameter of an hydrogen atom. Is it clear, students? Why Moore's law cannot move into errors of error? Why we cannot continue with the prediction of Moore's law for infinite amount of time? Because the transistor channel length, or more precisely the size of a transistor, cannot get reduced below the diameter of an hydrogen atom. That is the smallest elementary size which can physically exist. Yes, am I audible?
Yes, sir. You are
Yes, sir.
So, did you understand why the deviation of Moore's law took place?
Yes, sir.
Because reducing the size of the transistor went since decades, and ultimately we have reached such a critical size of the channel length of a transistor that spans with few nanometers. Further reduction of the size will just create a nuclear fission, because you cannot move beyond the diameter of a hydrogen atom for any kind of a device made of atom. And ultimately, the transistors which we built are made of semiconductor elements, so they are made of a number of atoms at the end. Am I clear enough?
Yes, sir.
Okay. Now there comes another question in our mind. Why the number of transistors within any IC or VLSI chip matters so much? because other than the transistors, also we have plenty of passive elements uh, or active elements such as diodes, passive elements such as resistors, capacitors, and so on. But why this number of transistors? We are always referring to number of transistors. Even while we understood the generations of ICs, we use the number of transistors to figure out what is the scale of them. So why we are always referring to the number of transistors?
So because the transistors can be combined to generate the different components like diodes and all those stuff.
Exactly. Now let me elaborate a little bit more. As transistor is an active electronic component or active electrical component, so the power consumption of any integrated circuit which is incorporated depends on its number. So ultimately, transistors are active electronic components. Transistors are active electronic components. And so the power consumption of any integrated circuit depends on the number of transistors. So these numbers plays the most vital role in determining that how much is the density which IC is made up of, or rather what will be the amount of energy it consumes to play an active role in its operation. Now, I am always referring since the last day the term transistors, but have you learned transistors in any of your semester curriculum?
Sir, in a basic layman way, in the paper of electronics, it was an easy paper actually. Over there, we have learned a bit about transistors.
It was a easy paper or a tough paper?
Sir, it was kind of easy paper, not very much
Not
tough.
past year actually. Not
Okay.
also.
So what kind of transistors you have learned?
So like CMOS transistors, SMOS transistors, those sort of things.
So you have learned this MOS devices.
So not in detail, just the definition kind of stuff. Like
Okay. So transistors can be broadly classified into two classes. One is BJT or bipolar junction transistor. Another is state field effect transistor. Usually within integrated circuits, we do not use bipolar junction transistors. We use field effect transistors due to some reason. We use field effect transistors within ICs, not bipolar junction transistors, due to the following reasons. The first one, field effect transistors are unipolar devices. So, what is a unipolar device? Here, only majority carriers control its operation. The second reason is field effect transistors are easy to fabricate than BJTs or bipolar junction transistors. The third reason, field effect transistors exhibit a high amount of input resistance. So typically in mega ohms. So a high amount of input resistance will lessen the amount of input current, and thereby it will be very appropriate for designing low power devices. So the fourth point is field effect transistors are less noisy. Less noisy. What do you mean by this term noisy? Anyone? Student? What is the meaning of this term noisy?
Sir, errors in the data which it produces, or the errors in the values that it produces, that's are less
Yes,
compared to another. Or
electrical interference are very less. Electrical interference are very less. So field effect transistors can exhibit a high amount of reliability than bipolar junction transistors in terms of its operation. So these are the few points which, if you remember, that's fine. That why we use field effect transistors rather than bipolar junction transistors for designing integrated circuits or manufacturing integrated circuits. Now, field effect transistors can be of again two classes typically. Field effect transistors can again be subclassified into two types: junction field effect transistors and metal oxide semiconductor field effect transistors or MOSFET. And again, due to some advantages, MOSFETs are used to design IC. Therefore, in the next portion of our lecture, we will try to concentrate on how a MOSFET works or how it looks like, everything. The physics of MOSFET transistors. So just concentrate to what I say and what I write down in the whiteboard. It will be practically very clear and elusive to all of you. So let me first try to draw the physical structure of a MOSFET. Again, MOSFET have certain classes, okay? Those things will come afterwards. First, let us try to understand how a MOSFET works. So take the first three alphabets, M, O, S. What does it signify? Metal, oxide, semiconductors. These terms are very significant while I draw the structure because the first three alphabets define the physical structure of the model. This is a metal layer. Next is a oxide layer, and then comes the semiconducting layer. Typically, MOSFET is a three-layered device. MOSFET is a three-layered device. So we have a metal layer at the top, below we have a oxide layer, and just below that the whole substrate is made of a lightly doped semiconductor. So let us try to redraw, or rather complete the drawing. And only these three layers, and typically these kind of well regions are not sufficient for operation of the or of any active device. You need to connect the metallic lead so that you can provide the potential. So you need to connect metal lead. So this kind of electrodes are connected, two with this P plus well region and one with this metallic. So this is also a metallic layer, but still you need a electrode to get connected so that it can be connected with the battery as and when required. Typically, one of these well region is termed as source, another well region is termed as drain, and this lead coming out of the metal is nothing but the gate. So the metal layer is the gate layer. One of the P plus layer is the source layer. Another P plus layer is the drain layer. And each of these P plus well region is carved out from an N-type substrate. Now the question comes, what are these symbols P plus and N signify? Anyone who remember your introductory class in electronic devices? Or maybe class 11, 12 high school semiconductor physics. What is N and what is
Sir, P-type semiconductors and N-type semiconducting material.
yes? What do you mean by that?
Sir, in P-type, the doping was in such a way that it was having more of protons.
Protons. There is no concept of protons here.
Something with boron or something. Sir, I am not exactly remembering the exact thing.
Okay. So before
Sir,
getting into the detail, yes, tell me.
sir, P type is which valence is mainly 3, or N type which valence is 5?
Now we are dealing with semiconductors. Any kind of semiconductor, what kind of semiconductor we use? Any idea what elements we use as semiconductor?
No, sir.
Yes, exactly. Semiconductors, there's a scope of using either germanium or silicon, but we use nowadays silicon. What is the reason for that? Your voice is breaking, I think. Silicon can be extracted from its compound called silica, which is plenty available within sand. So the cost of using silicon as semiconductor material is very less. Okay, this is the first point. Why we use silicon than germanium. The second reason of using silicon is what you mentioned. Silicon is thermally more stable than germanium. why this thermal stability is needed? As integrated circuits are mostly used within several military applications. To a high degree of thermal tolerance is required. Is it clear? Yes, students? Am I audible?
Yes.
Yes, sir, audible.
Okay. What is the daytime temperature in third desert? Any idea?
Sir, 55 degrees Celsius.
It is more than 50 degrees centigrade at least. And what is the nighttime temperature of Siachen Glacier?
Sir, minus 60 is in
Minus
winters.
75 degrees centigrade, almost 60 to 70. So all of the integrated circuits should be operational in this environment. Be it fitted within a Arjun tank practicing in a third desert, or within the howitzer machines which are installed in Siachen Glacier. All integrated circuits must be operational. So it requires a high degree of thermal tolerance. Is it clear? So again, let us move to the diagram of MOS transistor. So here, semiconductor means nothing but silicon. An N-type semiconductor means a silicon, lightly doped silicon, and the doping concentration is with 3 electrons. So it is N-type. P plus type silicon means a highly doped silicon, but the doping polarity is higher density of holes. So we do not use the term proton because proton is a subatomic particle. Proton is a subatomic particle with a certain degree of actual mass, whereas holes are deficiency of electron and it doesn't have any actual mass, it have only effective mass. So N-type silicon signifies lightly doped silicon and doped to it with 3 electrons. Whereas P plus type silicon signifies highly doped silicon and doped with significant amount of holes. Again, we come across two terms. Electrons, they are subatomic particles. And holes, nothing but deficiency of electrons, mind it. Holes are typically not any orthodox particle, rather it is deficiency of electrons. Now the question comes how this doping takes place. You must revise that how the doping takes place, otherwise there will be many nicks and grips of the operation within MOS which will be beyond the reach of understanding. So anyone who remembers how a doping can take place? Structure of a silicon crystal.
So maybe boron or phosphorus used for out.
What is this bonding? Exactly, covalent bonding. What is the valency of silicon? Valency of silicon? 4. So what is the outer orbital electron number?
4.
Exactly. So valency of silicon is 4. Therefore, outer orbital number of electrons equals to also 4. If that is so, then each of these free electrons, or rather each of these outer orbital electrons, can take part in one of these covalent arms. Yes or no? So these electron is coming from these atoms. So this atom has these electrons taking part in the covalent bonding, along with its neighboring silicon atom, which also provides another outer orbital electron to form a single covalent bond. Is it clear? Is the diagram clear? How many students are present in the class? 21. Who is responding? Priyapratu?
Yes, sir.
Yes, Aurobindo?
Yes, sir.
Deepak?
Yes, sir.
Isha?
Yes, sir.
Madhumay? Mosam?
Yes, sir.
Nawaz?
Yes, sir.
Megha?
Yes, sir.
Paulami?
Yes, sir.
Priyapratu?
Yes, sir.
Purushottam? Purushottam Kumar? Devarti?
Yes, sir.
Amanita?
Yes, sir.
Savnik?
Yes, sir.
Steve?
Present, sir.
Sauma?
Yes, sir.
Saurabh?
Present, sir.
Murthy?
Present, sir.
Priya,
Yes, sir.
Vijay Kumar, are you listening? Everyone?
Yes, sir.
Yes, sir.
Yes.
Yes, sir. Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
So this is a structure within a silicon crystal, a very small cross section where you may find that silicon atoms are within covalent bonding with neighboring silicon atoms. And the bonding takes place due to its availability of outer orbital electrons, which are four, and so four neighboring silicon atoms forming a covalent bonding ultimately creates the equilibrium with the existing centermost silicon atom, which now can justify the requirement of 8 stable outer orbital electrons. Is it clear? Is it clear?
Yes.
We are very much within atomic physics. If it is clear, I will move into the next question. Tell me.
Yes, sir.
Yes, sir.
Okay. Now, what we will be doing is we shall be replacing one of these silicon atoms. So, let us replace the centermost silicon atom and see how it figures out. So, this silicon atom Si is replaced with a trivalent atom. Name a trivalent atom.
Boron.
Boron.
Okay. Okay. Phosphorus is trivalent.
5 atoms.
What is phosphorus? What is the oxide? What is the oxide of phosphorus? What is the oxide name of phosphorus?
P2O5.
P2O5. So what is the valency of phosphorus? 5. The valency gets crossed, right? Yes or no? Creating the
Yes, sir.
empirical. What is the compound of boron? Oxide of boron?
B2O3.
Exactly, B2O3. So whatever with the valency that gets crossed while you write. Okay. So trivalent atom, boron. If the centermost silicon gets replaced with boron, what will be the structure of this crystal which I have drawn? Let me redraw it. Boron. Rest of the four are silicon. Each of these neighboring silicons provided an electron. Now, when there is a provision of boron to provide similar number of electrons, boron also tries to provide, but it gets exhausted with only 3 electrons. So here, so this becomes vacant. Because boron has within its outer orbit only 3 electrons, which it provides to 3 of the neighboring Si silicon. But the fourth neighboring silicon doesn't receive the contribution of boron. Am I clear or not?
Yes, sir.
right? So this is just a small section of your silicon crystal. A silicon crystal can have hundreds of such kind of structures within it, within the solidification structure. So there, if you replace few silicon atoms, maybe within hundreds of silicon atoms, you replace 10 to 20 of silicon atoms, using 10 to 20 of boron atoms, then there will be such kind of 10 to 20 number of vacancies created within the covalent bond. So, absence of electrons. So, this phenomena of absence of electrons is nothing but holes. So, as you replace more number of silicon atoms by boron atoms, more will be the number of holes. More will be such kind of vacancies created within the covalent bond. Is it clear?
Yes.
Yes, sir. Yes, sir.
Is the write-up visible? Is it visible?
Yes, sir.
Okay. Now let us try to figure out just the opposite thing. If you replace a silicon atom with a pentavalent atom, if you replace a silicon atom with a pentavalent atom, then how it looks like? So let us replace the centermost silicon atom with a pentavalent atom called phosphorus. Sorry, I have written here. So if you replace it with phosphorus E and try to form the covalent bonding, what you will find, each of the neighboring silicon gives its contribution of a outer orbital electron. Now when the term of phosphorus comes, it also contributes its outer orbital electron, and even after contributing 4 outer orbital electrons, what is found, another outer orbital electron remains without any covalent structure. Without being part of any covalent pair, this remains extra outer orbital electron coming out from the phosphorus atom. Clear?
Yes.
This is nothing but a free electron. This is nothing but a free electron which can move freely within the silicon crystal. Am I clear? So, more you replace silicon atoms with phosphorus atoms, higher will be the density of free electrons within the crystal. Mind it, the crystal is a silicon crystal. Do not doubt its effectiveness. That is, of course, a silicon crystal. So, ultimately, the material is semiconductor material, but it is not a pure semiconductor. It is either doped with a trivalent atom or it is doped with a pentavalent atom. Doping with a trivalent atom will create holes within the silicon crystal. Doping with a pentavalent atom will create free electrons within the silicon crystal. Right? So insertion of either a trivalent atom or a pentavalent atom within a pure silicon crystal is termed as doping. Is it clear? Now, depending on the doping density, depending on this doping density, there can be two types of doped semiconductor, lightly doped or heavily doped. So when you use like this N-type silicon, this is example of lightly doped silicon. Now the doping is here it is doping using pentavalent atoms, and so N-type silicon, 3 electrons are available. But when you mention P plus type silicon, it is heavily doped. Now, as because it is a P type ultimately, that means here doping is done using trivalent atoms. So excess amounts of holes are infused within it. Is it clear?
Yes.
Any confusion? Anyone can speak out of what I have told today throughout the past 1 hour. Tell me if there is any confusion regarding. Because ultimately we will be moving into this device. Now, structuring this device, again I am repeating, it is a 3-layered device. There is a metal layer at the top. Then comes within the middle is the oxide layer, and below the oxide layer is the semiconductor layer. Now, when I am mentioning the term layer, it can have different categories of doping within that layer, especially for semiconductor. For SiO2, it is an insulating layer. For the metal, we do not use the term doping in any sense. But within the semiconductor layer, there can be several regions created due to the process of doping. So there are 2 P plus regions created within a N-type substrate. So here doping with pentavalent atoms creates a N-type substrate in a very light manner. If you infuse doping in a much higher concentration with trivalent atoms within a specific or within 2 specific regions of N-type substrate, you can create 2P plus well regions or 2P plus regions. So one of the P plus region is termed as source, another P plus region is termed as drain. One thing very interesting, if you just notice this layered structure of MOSFET, if you draw a perpendicular right from this gate electrode downward, for example, let me draw it virtually. So if you draw these lines, right, what you can see, notice, what you
It's
can notice,
symmetrical.
exactly, both of the sides are physically synonymous. If you just cross-section these into two parts, right from the center of the metal layer till the down, you will find both the sides symmetrical in terms of its physical relevance. So MOSFETs are symmetrical devices. MOSFET is a three-layered device. MOSFET is a field effect transistor. MOSFETs are also symmetrical devices. Now, with the term symmetrical, we are very well within our limits to nomenclate one of these P plus region as source, another as drain, and vice versa. So you could have used this as drain and this right hand portion as source also, because MOSFETs are symmetrical devices. Any of the P plus region you can consider as source, any of the P plus region you can consider as drain. But for our example, to make you understand the operation of this device, I have to consider one particular end as source, another as drain. I have considered the left hand portion as source and the right hand portion as drain. But as because most or metal oxide semiconductor field effect transistors are symmetric devices, you can consider either way around also. Is it clear? Tell me. So, shall I continue with the physics of MOSFET in today, or I shall leave it for next day's class? Tell me. If you are overloaded, tell me. Because we are dealing with altogether a different kind of subject. Yes, tell me, because only one or two of you are interacting. So I cannot understand whether everyone is concentrating or not. Shall I continue in the next class?
Sir, I have a question. May I ask it?
Yes.
Sir, over a point you have mentioned that the FETs have high level of input resistance. So my question is, when there is high resistance, we know it generates a lot of heat, and we are talking about a lot of FETs in the IC. So it will generate a huge amount of heat within the IC. So won't that change the silicon, though it's have
Will
high
generate
thermal?
a lot of heat.
But how will the IC deal with that immense amount of heat?
No,
Like
why it will draw a lot of heat? Tell me that first. If it is high input resistance, why lot of heat will be generated?
Sir,
Just,
it will.
you just state Joule's law as per generation of heat is concerned. Do you remember Joule's law? The more it consumes power, the more it consumes energy, the more heat will be generated.
Yes, sir.
So if it displays a high amount of input resistance, low will be its input current. Generated heat is always proportional to the square of the amount of input current. So if you can reduce I, less I means less amount of H. Simple as that.
Sir, but H is equal to I square RT. We calculated in such a way. So if R is high, then H is also high by that logic as well.
Listen, H is proportional to R, but at the same time, H is proportional to I square. Now, there is a relation between R and I. We are forgetting that. So, if R increases, say 5
I
times.
decreases.
No, not
25
only I
times.
decreases. Yes,
25 times.
I decreases 25 times. Did you get it?
Okay, sir, I got this time.
Yes, everyone understood your friend's question and the answer related to that?
Yes, sir. Yes, sir.
Okay.
Hello. Hello, sir.
Yes.
Sir, I am present, but I can't speak my attendance because your voice is lagging a little bit at that time. So I think I have I say in last so.
Okay. I didn't call that attendance.
Okay, sir, sure.
Right. I was just checking that you are taking an afternoon nap or not.
Yes, sir. Yes.
I was just cross-checking that.
Yes, sir. Yes.
Okay, students, are you prepared to attend lecture classes maybe at 8 a.m.?
Sir, your voice is not audible properly.
Okay. Are you ready to attend lecture classes at early morning at 8 a.m.? Yes or no? Yes, Madhuma? Rest of you did not answer.
Yes, sir. No problem.
How many of you got jobs or sitting for the placement? Yes, every one of you are sitting for the placement interview?
No, sir.
Yes? No, it is obvious that many of the lateral entry students will not be eligible. I am asking the regular students.
Yes, sir.
So mostly are sitting for the placement interviews.
Okay. Which is the most sought after software destination hub in India? Yes, any idea? Which is the most sought after software destination in India, where most of the jobs are concentrated?
So Bangalore.
How many of you have been to Bangalore? How many of you have been to Bangalore? Anyone else? Anyone else? Yes or no?
No,
Sir, I
sir.
think no.
No, sir.
Okay. Do you know what is another name of Bangalore other than Garden City?
Silicon Valley of India.
Another name. These are all good things you are telling. Tell me something little bit grey. Okay, I am telling you. It is a city of traffic jam. Even to move 1 kilometer during office hours through your own car can take 2 hours. 1 kilometer, mind it. And Bangalore is a very spreading city. Most of the software companies from the heart of the city, it is around in a 30-kilometer radius. So what most of the software professionals do, either they stay very near to their office, which is nearly impossible because for Bangalore, those are situated in small satellite cities, those software companies, and those are not residential areas. So that option is not there. What is the second option? I have seen most of the software professionals, many of them are friends to me. They just start their journey from home to office at 6 a.m. or 6:30 a.m. so that they can reach within 9 a.m. Even after attending late night calls from their overseas clients. A person working in Ericsson, now he is in a very senior post, a good friend of mine, he receives calls from Sweden in Indian Standard Time, maybe 12 o'clock, right from 12 o'clock to 2 a.m. Even after that, he needs to move to office and starts from home around 6:30 a.m. Did you hear what I said?
Yes.
Saurabh?
Yes, sir. I heard it.
So it's
I,
better that you prepare for your professional life right from the fourth year itself. So I know there will be many of you who still do not wake up from your sleep at 8 a.m. morning, but it's high time to pull up your socks if you need a good professional life in future. So maybe not tomorrow, but maybe in some of the days I can tell Isha that please arrange a class from 8 a.m. Isha, is it possible, right? Isha?
Yes, sir.
Thank you.
okay, sir, not a problem.
Thank you. Have a good day. This is all
Thank you,
I
sir.
have for today's discussion. Thank you.
Thank you, sir.
Thank you,
And
sir.
Isha, just
Thank you,
send
sir.
me the attendance. You just get the